Can you
Okay,
see this?
I can see this.
Okay, go ahead.
So I'd like to thank Ted for taking the time to create this brief for us and to present it to us today. I think without further ado, Ted, I'll hand it over to you.
Okay, thank you, Mark. Thank you, Millimeter Wave Coalition. Pleasure to be with you. To talk with you about a theory that actually I've been working on with several generations of students since about 12 years ago. I call it the consumption factor theory. I don't know if this is the right name, and you'll see that we're kind of figuring it out over the last 10 years, but I think we finally have something that is baked and could be used by the industry to focus on a key issue that we face in wireless, which is how to reduce wasted power and maximize energy use, and how do we as engineers communicate the efficiency of the signals and systems, devices, and circuits we make. So I'm introducing today, and it was just published in December, what we've kind of come upon, these two metrics, waste factor. I put F, that should be W. Silly me, I'm gonna fix that right now because there's a reason why I put F, because it's like noise figure, but you're gonna see the exact mathematical procedure that Harold Freese did 80 years ago to create noise figure creates waste figure, or noise factor becomes waste factor. So I'm going to introduce waste factor, W, and consumption efficiency factor, two new metrics that I think will be key for all of us to start using in data sheets, spreadsheets, textbooks, and how we evaluate the power efficiency of devices. This is why it's important. We looked at this at the Brooklyn 6G Summit about a year ago. The Brooklyn 6G Summit last year was focused on sustainability. And 6G, with the pervasive deployment of picocells, small cells, IoT, is going to become about 20% of the global energy consumption. Our industry will be 20%. I don't know if you know this, but right now the biggest industry consumption is the clothing, apparel industry. To make nylon and dresses and shirts consumes almost 20% of the power grid in making those materials, believe it or not. But our industry will be 1 out of every 5 watts consumed on planet Earth in 10 years. This is a huge issue. So why is it that we as engineers don't have common metrics that we all can put on data sheets and can all use in writing our papers to determine the energy efficiency and how much waste there is in the power? So that's what this talk is about, introducing this new framework, which I'm very excited about. I think we really need it. So this all started back in 2011. You can see the germination of this idea back in this paper that my students and I at UT wrote, kind of predicting the millimeter wave future, mobility at millimeter wave. It's really one of the first documents in the world. Samsung and I were both at the same time predicting this future of millimeter wave. And buried in the back of this paper is the early start of this consumption factor theory. We gave it its name there. And then in 2014, James Murdoch, a great student, developed the consumption factor theory in a very detailed way. And this was the genesis of making this common metric, these two metrics, one that deals with wasted power and one that deals with efficiency, that is, how many bits can we send for a given joule of energy. The waste factor W has to do with the waste in a cascade of circuits, and the consumption efficiency factor has to do with the power efficiency, how much bandwidth of communication do we get per given joule. These are the two metrics I'm talking about. And you can see in this paper in 2014, down on the bottom left, we hadn't come up with the right name yet. We called it power efficiency factor, but that's now the consumption efficiency factor, because it wasn't really power, it was energy that was the metric. So we're still figuring it out, but 2014 paper has the root of this theory. And then finally, a few months ago, we published in the IEEE Wireless Communications magazine the transition to what I think are the final values that we can all start using. And I would really encourage us in our papers, in our patents, in our products, to start using it because we need it. The world needs a common language to discuss how much waste there is in a cascaded system, to compare our designs against one another.
Ted, I'm sorry to interrupt. You're still on the first slide that's being presented. Was that your intention?
No, I've changed a bunch.
I think we're seeing the irregular view. Yeah.
Okay, so let me do this. How's that? Is it changing? Thank you.
Yes. Now, yeah, we're on the slide of energy sustainability and future.
Okay, I'm so glad you said something. So this was my point, that we're going to be 20% of the global consumption in 2030 with the evolution of 6G. So my point was, we have got to get common language, common metrics to use in everything we do. And this was the first paper I mentioned, 2011, where the genesis of this consumption factor theory began. When I predicted millimeter wave, we were really pioneering the millimeter wave vision and making the case for circuits, mixers, amplifiers, what the state of the art in semiconductors were in this paper, and predicting millimeter wave mobile. Of course, people thought we were crazy. But this is buried in the back of this paper, is the start of this consumption factor theory. And then this paper in 2014 is where James Murdoch and I really put the math down to show how Shannon's capacity theory and the consumption factor theory all merge together to give these two metrics. One is waste factor and one is consumption efficiency factor. But we didn't call them waste factor and consumption efficiency factor. In this paper, we called them H, variable H. That was waste factor. It turns out it's the inverse of H. And then we called it power efficiency factor on the bottom left, you can see in the abstract. But we've now called it consumption efficiency factor. And here is the paper where we define this. It's December 2022, Wireless Communications Magazine. And this is the paper to read to get an idea of the power of this and the value of this. And I'm hoping all of us adopt this because our planet needs it. And there is not anything that exists right now. I've talked to circuits experts. I've talked to systems experts. I've talked to computer engineers that design data centers. And there's no common metric at all in all of engineering to quantify the power efficiency or waste and the amount of power per amount of joules, bandwidth per joules we get in a communication link. So this is our effort to define this. And what I want to do is I want to go back to Harold Freese 80 years ago, 1944, and take us through something we all use today. We use noise factor. We use noise figure. All of your companies either make or buy or use devices that on their spec sheet have a noise factor. You pay more for a lower noise factor. F, this wonderful noise factor, was developed by Harold Freese in the 1940s when signal to noise ratio was a premium. In that world in the 1940s, signal to noise ratio was the biggest challenge. Noise was our enemy of the planet in 1944 when vacuum tubes were used. You had all kinds of noise. Noise from tubes, noise from atmosphere. You had narrow bandwidth signals. You were doing telephone across the ocean. Satellites hadn't been invented yet. So signal to noise was the enemy. Noise was the enemy. And Harold Freese figured out a way that all of us can discuss noise and the noises of a cascade or a device. So we actually went back and looked at this in 2011. And what's amazing is this consumption factor theory creates W, waste factor, which is directly analogous to noise factor. It's exactly the same math in a cascaded linear system. Exactly the same math, which you're going to see. So everything that applies to noise factor applies to waste factor. So today in 2023, power consumption, energy efficiency, climate change is the enemy of our world. So we need a factor now to categorize the waste in a cascade, just like Harold Freese realized we needed to figure out noise factor. Now, back in the 1940s, receivers cared about the signal to noise ratio. Finally, at the receiver, you cared about what was happening at the receiver. So signal to noise ratio was always looked at to the input. So Harold Freese could have done his math on noise factor referring noise to the input or noise to the output. He defined it as noise referred to the input, so that if you knew the receiver signal at a device, an antenna, And through an amplifier, you could eventually figure out what it was at the detector. So here's the bottom line. Noise figure, Harold Free's development figured out that if F is 1, the cascade is noiseless. F equal 1 is the perfect no noise cascade or circuit. That is, the input signal noise ratio is equal to the output noise signal noise ratio. And if F is greater than 1, there's some additional noise that's induced in the cascade or circuit because of the circuit. And the key things that Harold Free realized was that it's the gain of a device in a cascade and the amount of noise produced by the device in the cascade that are the only two key parameters that determine noise figure for any cascade. In fact, here's the math from the original paper. You have your input signal to noise ratio, and I realize on this graphic on the far left, it says source, and you have output circuit. We should have made that a receiver. That should be a sink. The arrow should go the other way. The students, I realize, put the arrows going the wrong way. But we're interested in the input signal noise ratio referred to what's coming from the far right into the circuit. So you have something coming in from the right, going to the left, and these signal noise ratios are getting worse and worse and worse because each of these devices in this cascade are adding noise. The bottom line is the noise factor of the cascade, Harold Free showed in 1844, is related to the noise factor, or the amount of noise in the first component closest to the source, plus F2 minus 1 over the gain of that first device. So there's a cascade effect where all you have to know is the key figure of merit, noise figure, and the gain of the preceding stage. And the beauty of this is once you have a cascade of devices, if you know the noise figure of each device, then if you have the gains and the noise figures, you can figure out the total noise figure, the total degradation to signal noise ratio over the entire cascade. And remember, this is the key thing, that what is F? F is basically the amount of additional noise contributed by each device. So noise factor is the beautiful figure of merit that Harold Frees figured out for all of us to use to figure out how much additional noise is used. And what we found is we can do exactly the same thing instead of noise, but with power. So if you consider power consumption of anything we use, a cell phone, a circuit, a system, a network, a cellular to mobile link, the power consumed in any cascade, device, circuit, or system can be broken into the superposition of 3 power levels. These power levels all compose the entire power consumed of any system. First, you have the power that's delivered on the signal path. This is the cascade of devices that Harold Frees used in computing his noise. That is, P signal is going to be the power from the source to the sink carried along to each device that has information. So that's P signal. Then there's P non-signal. P non-signal is a power that is critical to delivering that signal across the cascade, but is not on the signal path itself. For example, consider an oscillator. A local oscillator is vital to supplying a mixer, the up converter or down converter signal. But it's the mixer that's carrying the P signal. The local oscillator is a vital component in the transmitter or receiver, but it's not on the signal path. Nevertheless, it consumes power. So that's an example of P non-signal. And then the third component, P non-path, is all the power in a system or circuit that's not used to carry information from one cascaded component to another. Think cooling fans in a base station, display on a cell phone. Think a heat sink. So you have P signal and P non-signal, which are vital in every communication link. And then you have P non-path, which is all the ancillary power consumed by components that don't contribute to the signal along the cascade. Now, what's really interesting is when you break the power up this way, you realize there's only 2 power components that we can care about to move the energy along a cascade, just like Harold Frees was interested in studying the noise buildup over a cascade. So if we just consider P signal and P non-signal, these are the two signal components that have to do with conveying energy across a cascade, across a network. There are two key parameters, gain and efficiency. It makes sense that power efficiency will be the power used to generate the signal in a device versus the power of the signal and the non-signal. Obviously, efficiency, eta of 1, means that all the power applied and used by the device or cascade is produced at the output. You lose nothing in the generation or creation or movement of that energy through the device. And gain is simply the output versus the input, exact same gain that Harold Freese used. When you do this, you can look at a simple IoT transmitter given here, and you can see there's a source input. You don't worry about the source. You just look at the cascade. You look at the mixer and the power amplifier and the oscillator. And what you can see is you have the oscillator is on the non-path. The mixer is on the path, so it's going to have a P signal and a P non-signal, and you can see that right there. So the mixer has P signal and P non-signal because it's on the path. The power amplifier has P signal and P non-signal. And the bottom line is we have a gain and efficiency for the mixer and the power amplifier. Now, what's amazing is once you define these two simple components, these two simple metrics for each device, gain and power efficiency, which are on every spec sheet of any device made. So using what's already known about products that go in a cascade or circuits, gain and efficiency, Murdoch in the 2014 paper developed the power efficiency factor, H, which is less than equal to 1. And on our 22 paper, we realized that refiguring the math and going through this very carefully, my students realized that the reciprocal of H in our 2014 paper is W, which means it's greater than 1. So the power waste factor, W, is a value greater than or equal to 1, which is the metric, the figure of merit we can all start using to quantify the amount of power wasted in a cascade or a circuit or a system or a network. In fact, here's the mathematical derivation. It's just like Harold Freese. The power waste factor is simply the ratio of the power consumed by the signal path components over the useful signal power delivered. Referred to the output, we refer it to the output because it's measured power out that we can measure in a lab. It's the measured output that will come out. And so just like Harold Freese found out that important component to reduce the noise figure was that device closest to the input signal. You want a low noise figure on the preamp. Similarly, power waste factor shows you want the most power efficient component to be the highest power consuming or highest power radiating component, the power amp in a transmitter. So using this math where W is simply the power consumed over the output signal power, you can realize that the total power consumed by the system is simply going to be the system power that's added plus all the non-signal power you add at the end. In other words, this W takes care of all the power waste of any device that's on the cascade. And then you just add up all the ancillary powers, the heat sinks, local oscillators, the display. And this is a way to get a total power consumption of any system in any network. So with W, the new metric for wasted power, just like F was the additional noise added, we can start looking at the math to figure out this definition of W. And I won't do the math here, but it's exactly like Harold Freese noise figure, except now instead of added noise, we're looking at added power, added signal power. Look at equation 1 on the far right. Added signal power by the device along the cascade is the power contributed by the device. And the question is, how efficient is that contribution? The efficiency of how much is wasted in delivering that added power is defined by eta, the efficiency. So using the equation, you come up with the total power consumed is related to the output signal power of 1 plus 1 over eta minus 1. That's equation 4. And using the definition of waste factor, what you find out from our 2014 paper, this is exactly 1 over H, which is W. That is, the W of a device is 1 over the efficiency. The waste factor is 1 over the efficiency. And log of waste factor is waste figure. 10 log 1 over eta is the waste figure. So this is beautiful. If we know the power efficiency of any device, we've defined the waste factor of any device. And just like in Harold Freese's math, how in a lossy system, the noise figure is equal to the attenuation. Remember that from senior year? The waste factor, exactly the same way, the waste factor of attenuator is equal to the loss of an attenuator. We derived this in the 2014 paper. And so now you can start looking at a cascade, and the math is identical. Instead of added noise, we're interested in added wasted power. So the exact same math that we saw in 1944 leads to the cascade, where the power waste factor of a cascade is equal to the waste factor of the device closest to the sink, that is at the output, plus W1 minus 1 over the gain of the previous device. So just like noise figure, we now have a new metric, the power waste factor, which represents the ratio of the power consumed by the signal path components to the useful signal power delivered by those components in the cascade. It's exactly the same. Instead of F, we use W. W being bigger means higher power wasted. And the gain of the components closest to the sink, that is at the output, where you want the maximum power, influences W the most. And what's beautiful about this is once you use W, we can now figure out for any system we build the total power consumed by using this elegant power waste factor times the signal that came out of the device, and then add up all the non-path components, all the ancillary components not on the path. I want to make an important point here. In most very low-cost IoT devices, there's going to be very few non-path components. So the power consumed is primarily going to be the signal path components. However, in a base station or something that's got a lot of overhead or a lot of CPU, baseband processing, video graphics, the cell phone industry, most of the power consumed will be the non-path components. Nevertheless, if we care about every joule of the planet, it's important that we have this common metric W, a waste factor, to be able to use to compare our cascaded systems that carry the RF component. In a base station, the power transmitted by the transmitter is often a low percentage of the total power for the heat bill being paid by the infrastructure provider. Nevertheless, we want to save every watt we can. And so W is valuable in all systems, just like noise figure, I claim, is valuable as a metric, a currency that we talk about in comparing for all systems. So here you have it, a comparison. 1944, the figure of merit to quantify noise referred to the input is given at the top, Harold Freese. And now we have 2022 in the December magazine, a figure of merit to quantify power wasted in a cascaded system. Exact same kind of math, and you can see that here it's referred to the output. So let's put this to use. Just like we saw in linear systems, and this is in our 2014 paper, a cascaded system, cascaded subsystems, you can still use the same theory. So if you know the W of one system and the W of another subsystem and you cascade them, it's very simple to use the exact same mathematical formula, just like noise figure. And when you want to look at the propagation channel, this is beautiful. Since a wireless channel behaves as an attenuator, the waste factor of a channel is simply the loss of the channel, the propagation loss of the channel. And there's a wonderful simplification you can make in this theory. Because if the gain of the receiver across a radio link is much less than the loss in the channel, that is, if the receiver gains much less than the path loss, which is very typical, then you can make a very beautiful simplification because of the math in the 2014 paper, and that is the waste factor of the entire link simply becomes the loss of the channel times the waste factor of the transmitter divided by the gain of the receiver. Such a beautiful, elegant way of characterizing the waste factor of an entire link, a transmitter source to a receiver sink. So, given this, I'm going to give you a test. Let's say there are two circuits that we design. Case one, we pick RF amplifiers, mixers, and bandpass amplifier, baseband amplifiers for mini circuits that have the given efficiencies. And case two, we pick different RF amplifiers, mixers, and baseband amplifiers. We run the math using these simple gain and efficiencies from the spec sheets of this homodyne transmitter shown in the left. Case one, we get a waste figure of 4.85 dB. Case two, these components we used, we get a waste factor of 5.41 dB. Which design do we choose to save the planet? Anybody? Tell me which design we choose. Shout it out. We want W to be smallest. Case one. Was that you, Mark?
Yes.
You get an A. Okay, great job. So you see, here's a way we can now talk about the power wasted in a cascade along the system. Notice the oscillator was ignored because the oscillator is not on the signal path or contributing to bringing the signal. It's an ancillary device. Obviously, the total power would simply be, you'd look at the output power of this homodyne transmitter, multiply it by W, and then you'd add the oscillator power to get the total power consumed of this product that you're making. But this is an example of how we can all use waste factor. And then consumption efficiency factor, which is really, really the key, because this tells us how many bits per joule we get or how much data rate per power consumed we get. This is called energy efficiency, but we call it the consumption efficiency factor because we called it the consumption factor theory. What this does is it computes the energy consumption using W. So now using W, if we all are using W, the waste factor or waste figure, as a common metric, a common currency of determining waste, you can use W very easily to compute the consumption efficiency factor. And the details are in that 2014 paper. So now let's put this to use now in a real system to start figuring out the consumption efficiency factor, which, remember, consumption efficiency factor is simply the bits per joule or bits per second per watt that a cascade, any cascade system, gives us. So it's relating the data rate carried to the power consumed. Data rate carried to power consumed. And it's going to be related to spectral efficiency, but this is a metric, an overall metric that allows us to quantify any communication system to see how green it is or to compare it with something else. So let's look at two systems, a 28 gigahertz, 400 megahertz band. This could be a cellular system. I've got numbers of antennas, base stations, power efficiency, mixers, insertion loss. I've got a low noise amplifier, figure merit. I've got a lot of stuff. And we did this example in the December 2022 paper for COM magazine, a wireless COM magazine. And if you want the details, we could provide that. But you can use the theory and then look at a 140 gigahertz system, which is going to have a 4 gigahertz bandwidth, 4,096 antennas. This is the future. This is 6G. And look at the power levels. You can see that we've got a large number of antennas. We're assuming equal PA efficiency, or a little less PA efficiency at 140. But take a minute and just think intuitively. If we're going to use much, much more bandwidth at 140, doesn't it make sense we're going to use a lot more power, right? I mean, the consumption efficiency factor has to do with the number of bits per joules, and obviously you're going to have a lot more bits at 4 gigahertz. So you're going to be using more power, but you're also getting a lot more antenna gain. You're getting a lot more antenna gain with 4,096 antennas versus 1024. So you're beating the propagation path loss with more gain. So you don't really know intuitively exactly how much more power 140 gigahertz base station to mobile link, which is what we're assuming here, including the propagation channel. We don't really know what's going to happen. Well, here comes waste factor and consumption efficiency factor to the rescue. And as we show in the 2022 magazine paper, when you put all this stuff in and we take a look and compare it, You can see power in watts consumed. This is assuming all the ancillary and on the path power. You get 5 watts consumed over this base to mobile link at 28 gigahertz versus 33 watts. So obviously it's a lot more power hungry on the uplink and also on the downlink. So we're having to pay a whole lot more power, total power consumed, for 10 times the bandwidth, 4 gigahertz versus 400 megahertz. In non-line of sight, remarkably, it's identical. The non-line of sight is identical. Why is this? Because the uplink and downlink have the same propagation channel, and because of that simplification of the path loss. What's fascinating, though, is in non-line of sight and line of sight, your capacities are very different. And this is using Shannon's capacity. Shannon's capacity, 4 versus 55 watts. I'm sorry, 4 versus 55 gigabits per second, and 1.73 versus 22 gigabits per second. So what you can see is you get about 10 times more data rate and maybe 15 times more. So you get a little bit more capacity in non-line of sight, but much higher data rates at 140 gigahertz. So you're spending about 6 to 7 times the power to get 10 times the capacity. And then the consumption efficiency factor, which tells you how efficient you are, gigabits per joule, is going up. So instead of 0.96, you're getting 1.64. By the way, I think this is an error at non-line of sight. I think the students didn't put in the right numbers here. This is an error. Non-line of sight should be consuming more power because the path loss is higher, even with the simplification. So I have to change these right here. But the bottom line is, in non-line of sight and line of sight, you can see you're getting, in non-line of sight, you're getting double the consumption efficiency factor. You're getting twice as more efficiency, bits per watt, or gigabits per joule. You're getting twice as much efficiency going to 140 on the uplink, at least twice as more efficiency on the downlink, and in the uplink, you're only getting about 70% efficiency. The bottom line is we're able to, the energy consumed per megabit at 140 gigahertz is reduced by about 60%, but we have to pay a higher power bill. So it's still hurting the planet. I guess the key to all this is, with using the waste factor theory, we were able to build a mock transmitter receiver propagation link, put in the values to get the system W's, and then it made it very easy to compute these values. And once you do this, you can start to compare the best or optimal use of efficiency for given bandwidth and varying bandwidth. And what you see is on the downlink, if you can get the consumption efficiency factor dialed in to be better than at 28, you use bandwidths greater than 500 megahertz. That is, there's a crossover point. If you use 140 gigahertz for all those inefficient power amps and all those antennas with loss, and you only use 500 megahertz or less, you're not any more efficient in power, but you're paying a bigger power bill because you're using more bandwidth. But if you can get the RF bandwidth greater than 500 megahertz on the downlink, you start getting a dividend. You pay less per gigabit per second, even though you're paying a bigger power bill. You're more efficient. So there's places to operate with bandwidths that give you the benefit of having a more efficient consumption efficiency factor. And similarly, in uplink, you can get greater bandwidths when you go above 2.5 gigahertz with these lossier, more antennas, which are lossy. You still are getting better in terms of megabits per second per joule. So megabits per joule. So using these metrics, you can start finding. In fact, we found that there's an optimal cell radius. An optimal cell radius at 140 gigahertz happens to be 67 meters, at where the consumption efficiency factor is maximized. Of course, these are simple studies, but they give you an idea of the value, the power, when we all use a common currency, W for waste figure or W for waste factor, and use consumption efficiency factor. These two metrics are key to being able to study things like this and trade-offs for power consumption. And the effect of cellular radius on the total network power consumed can be studied. I mean, this is pretty amazing. You can look at the total data throughput, total power consumed in the network, and then the total network consumption efficiency factor. So what you can see is data throughput for the smaller cell radius network becomes 18 times greater, leading to greater CEF when you optimize the location at 140 gigahertz. So there's a lot of future in this, I think. Think about this. Cellular base stations consume more than 50% of the power in a cellular network. You look at the spending of all the big carriers, nationwide carriers, and their electric bill is just incredible. So each base station has a carbon footprint. It's not insignificant. So if we evaluate the power waste factor W for base stations, we can help improve the efficiency. We can, in devices, every device, we can improve the power efficiency using W. So a waste factor, a power waste factor W, I think can facilitate decisions, trade-offs. You could look at base station sleep algorithms, energy sources, what kind of energy do you use? And I'd like to apply this to data centers, to computers, to CPUs, because the people that design these multi-thread computers, they have admitted to me that the total power they consume is always greater than what they model. They don't have models. They don't have language in how they're designing the edge servers. So I think this idea of breaking the power up into separate, discrete, orthogonal components and using superposition can be used to pick apart and really study and develop a common metric where we can do power designs of software, of multi-threaded things, of temperature regulation, power backup. These are all really heuristically done, and it's a problem for the industry. So I'll conclude with the power waste factor, W. It's a new metric. It's a general formulation to compare the energy efficiency or power efficiency, since energy is the ability to change and power is the flow or the movement of that energy. So it's a way to look at any cascaded communication system to compare its power efficiency or its energy efficiency. The power waste factor is a fundamental characteristic. It's exactly analogous to the noise factor. You just need to know the gain and the efficiency of individual components. Finally, using the waste factor theory, we defined consumption efficiency factor, which is other people have called energy efficiency, but we're calling it consumption efficiency factor because we call this the consumption factor theory. The consumption efficiency factor allows you to use W in the output power to figure out all the power on the cascade, and then you just can lump in, if you want, the non-cascade power. And it shows that using this consumption efficiency factor, you can start looking at energy efficiency and studying trade-offs like we did with the cellular system. And we showed a 60% savings as you reduce the radius. And then finally, the consumption factor theory, I think, can be used to explore RF energy harvesting techniques, IoT devices. I think it can design intelligent reflective surfaces. I think this is a fundamental approach, and I advocate you taking a look at it. Be happy to work with you on it, and I hope you found this of interest. And thanks to all the industrial affiliates who support our work at NYU Wireless. And there's a bunch of references here. I'll send you the slides if you want.
That'd be great, please.
References with links. But I think this is something that could really help our industry, and I hope you found it interesting.
Yeah, thank you very much, Ted. I appreciate it. It's a very interesting talk. I think we're about to run over time, but if you don't mind hanging on for a few minutes, if we have any questions.
Sure.
Any questions from the floor?
Hey, Ted, this is Greg Chumak. It just occurs to me, and I wonder how much you've thought along these lines about the potentiality for, kind of a two-pronged thing. One, in the private sector, requests for bids for various types of systems, starting to specify minimum consumption efficiency factors for the system in their request for bids, or maximum waste factors, however they wanted to do it.
Yeah, I think that would be great. Until this is adopted, until people don't even know about it, they won't use it. But absolutely, I mean, you see bids, noise figure must be so and so on a satellite system. Absolutely, I think if we're going to be conscious of consuming fossil fuels and renewable energies, I think our industry has to really take a look at this. We need to be cognizant of this. This is energy consumption, and I mean, I haven't seen a common currency or a figure of merit that the industry is standardized on. I looked and looked, and
Now,
this seems.
have you all explored the possibility of even looking from the regulatory side? For example, in an FCC licensing requirement, have certain minimum weight figures or maximum consumption figures as part of the requirements in a licensing situation for certain types of transmitters. For example, I'm just wondering if things like this could eventually work its way into the regulatory framework for a lot of wireless stuff.
Well, I'm not gonna recommend that. I'm a lowly academic, but I do think if we as a community start using it and see the value of it, it will emerge as a standard. And to me, there's a sense of urgency, just given what I heard John Holden say at the National Academy of Engineering meeting last week. He was Obama's uh, science advisor, and he gave a very scary, compelling hour-and-a-half talk. It was riveting, and it really motivated me. And then we did the Brooklyn 6G Summit on sustainability, and it further motivated me. It just made me realize we have to, as engineers in the technical community, start looking at this. When we publish papers or produce outputs, we just can't say, here's a result. We have to say how much power it consumed. And eventually that may happen, what you're talking about, but I think until we start using this and other people see its utility on the technical side, it'll never go anywhere else. So that's why I think this is a technical issue that we as engineering researchers, product managers, we need to start doing on our own. And then maybe it'll take hold in the bigger, grander regulatory and other areas, but and bids. But right now, I think we have to know about it and use it. See if I'm crazy or not.
Any other questions?
Yeah, Mark,
Ted,
this is Mike.
Go ahead, Mike.
Will this presentation be made available to the team?
Yeah, absolutely. I'll send the slides. Mark, I'll send the slides to you right after this.
Sounds great. Hey, Ted, I have one question for you before we,
Yeah.
as one last question on the talk. So it seems that the efficiency factor gains from the larger arrays at the higher frequencies, but we also use those larger arrays to overcome a greater path loss.
Right.
And so is that comparison? It almost feels like we're double counting it, or was that the same range or the same range in lambda?
No, what's really interesting, it's a great question, Mark. You're counting everything. You're counting less efficient power amplifier, so you take a hit. You're getting more gain, so you're getting a better lower waste factor in the channel. But you're getting everything's in there. You're not double counting. It's all, there's loss. You get more loss with each of the interconnects for those 4,000 antennas. So they give you a hit also in the waste factor. So it's all in there.
Okay.
And it's the bottom line, the path loss, whatever the path loss is, the path loss is. So it's what's beautiful is you're right. If we don't use all 4,000 antennas, we'd get a different waste factor. And so one thing we say in the paper is you can integrate over different states, or you could look at the percentage of time you have maybe all 4,000 antennas used and a percentage of time where the beam's smaller, and you can integrate that to get an equivalent W for the system. You know what I'm saying?
Great. Well, thanks very much, Ted. Then if we don't have any more questions, I will close the meeting for here, and I will send out the slides for everyone. And I did make a recording of this, so if you're looking for a recording, reach out to me, and I'll see if I can post that somewhere. All right.
Right.
Thanks very much.
Yeah. Thanks, everyone. Thanks for
Bye-bye now.
Thanks, Ted.